Hello and welcome to ACSC Academy. This is the part 4 of our topic Quadratic Equation from the NIMSET series. In this part, we will be dealing with the topics about the common roots and the factor theorem. It's really easy to score full marks in this topic because we often encounter questions from that and it's really easy to understand as well. So let's begin. First, coming to the factor theorem. We are already aware about this. We know it and we have been using it implicitly while solving the problems from the previous topic from the remainder theorem as well. But just for the sake of knowing the terminology, here we have the statement of this theorem that we have a polynomial p of x when that is divided by x minus a. Now what is it? A is some constant. So x minus a becomes a linear polynomial. So when a polynomial p of x having any degree, we are not concerned with it, when that is divided by a linear polynomial x minus a and the remainder p of a. Now, why the remainder is p of a? We have learned this from the remainder theorem itself. What did it say? That you have a polynomial p of x. If you divide it with x minus a, then the remainder left out would be p of a. This will be the remainder. That is what we learned from the remainder theorem. So now what this factor theorem is saying, that if that remainder p of a becomes 0, if the remainder becomes 0, then we can say that x minus a is the factor of p of x. Easy to understand, just as we have with the case of integers, that we say that a is divisible by b if the remainder is 0, or we can say that a is perfectly divisible by b if a modulo b equal to 0. That is what we use in the general logic. The same thing is put over here in the terms of polynomial, that we can say that a polynomial p of x is perfectly divisible by x minus a if the remainder, which is given by p of a, is 0. So if the remainder is 0, then we will say that it is perfectly divisible, or x minus a is the factor of p of x. In the same way, you can put the statement also as x minus a is the root of p of x equal to 0 if x minus a is the factor of p of x, which means, now if this is holding true, if x minus a is the factor of p of x, then what does that imply? That x minus a is dividing p of x, so x equal to a, or x minus a equal to 0. From here we come to x equal to a, and this x equal to a will turn out to be the root of p of x equal to 0, which means we had this polynomial p of x. When you equate that to 0, it will become an equation. For this equation, x equal to a will be the root. So what do we learn from this? The only thing, that you have a polynomial p of x, if it is perfectly divisible by x minus a, then you will say that x equal to a is the root of what? Of p of x equal to 0. And how do we check if it is perfectly divisible or not? Using the remainder theorem. We calculate the remainder, that is p of a, and if that is 0, then we will say it is perfectly divisible, otherwise no. So if you find out that it holds true, then you will have x equal to a as the root of that polynomial. So this is what we have all about the factor theorem. We already knew this and we have been using it implicitly, but just for the sake of knowing the terminologies, here we have covered it in detail. So the next topic that we have is about the common roots. We'll be dealing with the common roots of quadratic equations. So here we are having these two quadratic equations, a1x squared plus b1x plus c1 equal to 0, and a2x squared plus b2x plus c2 equal to 0. And their roots have been given as, for this first quadratic, let us call it q1 and this one as q2. For this q1, we have the roots as alpha and beta. while for Q2 we have the roots as alpha and gamma, which means you can see that this alpha is the common root. Only one root can be common in two polynomials. If both the roots become common, then those equations will become equal. Let us say, for example, let us take two roots as 2 and 3. If these are the two roots, then what will be the quadratic formed out of it? It will be x squared minus sum of roots, which is 5x plus product of roots, that is 6, equal to 0. So if roots are 2 and 3, then this is the quadratic that we get. Now if another equation Q2 also has the same roots 2 and 3, then we will get the same equation. Q1 and Q2 will become equal in that case. So here we are dealing with those cases in which only one root is common between two polynomials. So let us consider the roots of second polynomial is 2 and 5. Then in that case, what will be that quadratic become? It will be x squared minus sum of roots, that is 7 into x plus product of roots, that is 10, equal to 0. So here we have got two different quadratics, Q1 and Q2, which share one common root, which is 2. So this is what we are talking about over here. We have this, in general, we have taken two quadratics Q1 and Q2, which are having the roots alpha, beta and alpha, gamma. So alpha is the common root. So now if you have been given, what type of questions are expected from this topic is that we will be given two different quadratic equations and you might be asked to find out what is the common root between them. So if the two quadratics given are just simple like these we have an example, then what you can do, you can simply factorize it. For Q1 you will factorize it as x minus 2, x minus 3, and for Q2 you will factorize it as x minus 2, x minus 5, and you can straight away see that x minus 2 is the common factor, which means x equal to 2 will be the common root. But the thing is, it is not always easy or it is not always possible to factorize the two quadratic equations that are given to us. Or you can say that it is not always possible to actually find out the roots. You might think that you have been given two quadratics, Q1 and Q2. Let us find out their roots. For this you will get, let us say, alpha 1, beta 1, alpha 2, beta 2. So you will find out the roots of both of them and then you will check if there is anything common in them. Again, it is not always easy to find out the roots. You might need to go for that method which we have earlier discussed, that is minus b plus minus root over of dy. The factorization method might not always work, so you might need to go with the traditional completing the square method for finding out the roots and then compare them. So it becomes tricky and even time consuming. So is there any way using which you can quickly determine if the given two quadratics will have a common root or not? So that is what we have to deal with in this topic. So what we will be doing is we will try to solve these two equations together. How can we do that? Both of them are quadratic, but what if we consider them to be like the way in which we solve the simultaneous equations? In that lines, can we do something out of this? We can try to do something like, as we can see in the quadratic Q1, we have the middle term, that is B1, this B1 over here, and B2 in this Q2. What if we do something like we multiply Q1 with B2 and we multiply Q2 with B1? Then what will happen is that the coefficient of this x will become same in both the equations. Then we can subtract them and we can easily eliminate that term. So let's try doing it. We will multiply Q1 with B2, Q2 with B1, and then we will subtract both the equations together. So let's see how that can be done. We will do A1 B2x squared plus B1 B2x plus C1 B2 equal to 0. This is q1 multiplied with b2. Now q2 times b1, that will give us a2 b1x squared plus b2 b1x plus c2 b1 equal to 0. Now we will subtract them. This term will be eliminated and we will get a1 b2 minus a2 b1 x squared plus of c1 b2 minus c2 b1 equal to 0. So from that, what can we see? We have got the value of x squared from this. What is the value that we have got? We can just shift the terms on the right hand side and then we can write x squared equal to this entire term. When shifted over there, it will change its sign and that will become c2 b1 minus c1 b2 upon a1 b2 minus a2 b1. So we have got the value of x squared. But is it over? We are not done yet. Just by knowing the x squared, we cannot determine what will be the common root, because this x here represents both the roots, common roots as well as non-common roots. So if we have to know the actual value, we cannot simply substitute x equal to alpha and we can say that this is the common root that we have just calculated or the square root of this. That is not possible. We can do one more thing, which is we can have a look at this first term, the x square. Can we eliminate this term as well? How is it possible? We can multiply this q1 with a2 and q2 with a1, and let us try to eliminate the first term. Then let's see what do we get. By doing so, we will be getting a1 a2x squared plus b1 a2x plus c1 a2 equal to 0 and a2 a1x squared plus b2 a1x plus c2 a1 equal to 0. Now when we subtract them, the first term will be gone and we will get b1 a2 minus b2 a1x plus c1 a2 minus c2 a1 equal to 0. Now from here we have got the value of x. What is it? After shifting the terms, we get c2 a1 minus c1 a2 upon b1 a2 minus b2 a1. So now we have the values of both x and x square. But what we were actually doing, we were trying to find out the value of the common root, which is alpha in this case. So can we substitute x equal to alpha and say that both of these equations will be holding true for it? It means we have got the value of both alpha square as well as alpha. And we already know that alpha is the common root. But the values that we have got is in the terms of the coefficients a1, b1, c1 and a2, b2, c2. So we can establish some relation in between them. What we can do? We have alpha as well as alpha square. So we can equate both the things together. We can just square this thing out and we can compare both of them. Then we will be able to establish some relation between the coefficients a1, b1, c1 and a2, b2 and c2. And we will be able to conclude that when this particular relation holds true, then only we can have a common root between two quadratic equations. So let us try to compare this and see what is the result that we get. What we were trying to achieve, the common root is alpha in this case, so we will substitute x with alpha and we will have the value of alpha square as well as alpha that we have just calculated. And now we are simply going to compare them. This is alpha square and this is alpha, so we will square this thing and then we will compare these two. So here we have squared the lower term to get alpha square again. That is, for numerator we have simply done the square, but for denominator, as you can see, if you compare both of these denominators together, this is b2a1 and b1a2, but here it was b1a2, which means the terms are switched in their order. Here b1 a2 was at the end, here it is at the start. So we can simply flip that by taking a minus outside over here. Then both the denominators become same and we will simply square them. So now this is also alpha square and this is also alpha square. So we can definitely equate both of them together, and then we will be able to get a relation between all the 6 coefficients. And with that relation, we will come to the conclusion whether or not we have the common root, what is the condition that needs to hold true if two quadratics have to have a common root. So let us compare these two and try to get that relation. So here on the left hand side, we have the calculated value of alpha square that we already have. And on the right hand side, we had the value of alpha, which we squared, and then we are trying to compare both the terms together. As you can see, there was this minus sign at the bottom and then that was squared. So when we perform the whole squared over there, then this minus sign will be gone and we will be simply left with the same denominator on both the sides. So we can cancel out this denominator one time. This will become 1. And now we can simply cross multiply these, or you can establish an equality between them. How can that be done? We will keep this numerator as it is, a1c2 minus a2c1 the whole square, and that can be equated with the product of these two, b1c2 minus of b2c1, and this denominator which we already had, b2a1, or you can write that as a1b2 minus of a2b1. So this is the relation that we have established between all the 6 coefficients a1 b1 c1 and a2 b2 c2. What is the condition? That you need to have a1 c2 minus a2 c1 the whole squared equal to the product of these two, a1 b2 minus a2 b1 and b1 c2 minus b2 c1. When this particular condition holds true, then only you can say that the two quadratics q1 and q2 will have a common root between them. So this is the condition that you need to remember. But it looks difficult to remember. How can we remember the correct order in which the coefficients are there? So for that we have a trick, that how can we remember this particular relation. So let us see what is it. We can simply spread out all the 6 coefficients in this particular way. In the first line, we will have the coefficients of q1, which is a1, b1 and c1, and just below them we will have the coefficients of q2, which are a2, b2 and c2. Now what we have to do is, we will take the two extremes together. We can join these two extremes like this. And now the points which are being connected, we will simply write them down. a1 c2 minus a2 c1. These two together, a1 and c2, and then a2 and c1, these two together, the whole square. Now you might ask whether we should take a1 c2 minus a2 c1, or we have to take a2 c1 minus a1 c2. Now as you know, the order will not actually matter in this case because we are anyway performing the whole square. But just for the convention, you will start with the first row first, which means you will take a1 c2 minus of a2 c1. So now done with the first part. Now this will be equated with, for the part 2, what we will be doing is we will multiply in this particular way, the first x that we can make. What are the terms that is joining? a1 and b2. So now that will come next, a1 b2 minus of then these two, a2 b1. Done. Now the last term which we are left out, for that we will make this second x. In this way, the 4 terms that were remaining, we have made a connection like this between them. So now what are the terms that it is joining? It is joining b1 with c2. So we will have b1 c2 minus of b2 c1. So we have got the same relation over here, and this is an easier way of calculating it. We don't need to remember it that way. So So we'll simply spread out all the 6 coefficients in 2 rows, one below the other, and then we will just make out this cross lines A2, B2 and C2. We will start with the 2 extreme points like this. That is the first cross we make. Then in the second time we make this one. And in the third time we make the third cross like this. And whatever the points we are connecting, we can simply write them from top to bottom, subtracting with each other, and that is how we get the same equation. So this is a way for getting that relation, which will be used in order to check if the two quadratics q1 and q2 have a common root or not. So now, based upon this, let us check out some examples that how do we apply this practically. First example that we have from this topic, we have been given these two quadratics q1 and q2, and it is already mentioned that they have a common root. Now if this condition holds true, we need to find out the value of k, which is given over here. C2 coefficient has been replaced with k. We need to find its value in order to satisfy this particular condition that they have a common root. So now how can we approach this? There can be two methods. First, the traditional way, in which we can actually find the roots, but we do not really know what exactly is the common root between them. We can try to find out the roots for both of them, and then we can compare them to see which of them is common. So it is going to be lengthy and we are not guaranteed to get the correct answer out of it. The reason being that it is not always possible to factorize or find the roots of all the quadratics, and even if we are able to do that, we will not know which of them is the common root. So this way it is not encouraged to apply in this particular questions. But if you have been given the options and you are trying to eliminate them, then there can be some tips and tricks that we will be having a look at. But the formal way for solving such problems is using the relation that we have just derived, the relation between all the 6 coefficients a1, b1, c1 and a2, b2, c2. Using that relation, we will apply the condition that both of them have the common root, and then we will be able to get the value for k. So for this particular question, let us try solving by both the methods so that we can analyze which one we should go for and what is the difference that it creates. So going with the first method, that is actually finding the roots. Now coming to q1, let us try to find the roots of this quadratic. X squared plus 6x minus 91 equal to 0. Can we factorize it? Looking at 91, it seems that it can have factors 13 and 7, and for getting the sum plus 6, we will take 13 and minus 7. So yes, we have got the factors as x minus 13, x plus 13 and x minus 7, which means its roots become 7 and minus 13. These are the two roots for quadratic q1. And in the same way, q2 will also have two roots, but we cannot find them because they will come out in terms of k. So there is no meaning in finding the roots of q2 in terms of k because we will not be anyway able to do that. So what is the other thing that we can do? We can one by one assume that 7 is the common root, or we can assume that minus 13 is the common root, and then we can proceed because we do not know actually that which of them is the common root. Any one of them will be. So in case 1, let us assume that 7 is the common root, and if that is true, then 7 must satisfy this q2, which means if I substitute x equal to 7 in q2, then I will get 7 square plus 4 times 7 minus k equal to 0, which means 49 plus 28 equal to k, which means k equal to 77. So if 7 is the common root, then the value of k will be 77. But what if minus 13 is the common root? Then that will satisfy the quadratic. So let us also try doing that. If we substitute minus 13 as the value of x, then we get minus 13 squared minus 4 times 13 equal to k, which means k equal to 169 minus 52, that is 117. So if minus 13 is the common root, then value of k has to be 117. But now we do not know which of them is true. So what can be done? Should we apply completing the square method on Q2 and then check if we can get something? Let us try doing that as well, and we will note down these results over here. For 7 as the common root, value of k is 77, and for minus 13 as the common root, the value of k will be 117. So now we will apply the completing square method on Q2 to find out its roots in terms of k, to see if we can get something from that. So we will have the roots of Q2 as minus b plus minus root over of d, which means b squared minus 4ac upon 2a. This becomes, let us note down, a2, b2 and c2. a2 is 1, b2 is 4 and c2 is minus k. So we get minus b, which means minus 4 plus minus root over of 16 minus 4k, so plus 4k upon 2. This has to be the root for C2. So now how can we derive? It will have two roots, let us call that alpha and beta. We have got these as their values. So now the only option we are left with, we will try to substitute both 7 as well as 77 and 117 in place of k, and then we will solve this particular thing out and then check out if by substituting k equal to 77 do we get 7, by substituting k equal to 117 do we get minus 13. Then any one of them will be satisfied, and then we will be getting the common root. So this is how lengthy it is going to be, but anyway, let us try to do just for the sake of learning. The first time we will be substituting k as 77, then we will get minus 4 plus minus root of 16 plus 4 times 77 by 2. And when we solve this out, what we get is, it is minus 4 plus minus 18 by 2, which gives us two values, that is 7 and 11. So yes, by substituting x as 77 we have got 7, but does that mean that 7 itself is the common root? Let us also check for the second one. By substituting x as 117, then we get minus 4 plus minus root over 16 plus 4 times 117 by 2. This evaluates to minus 4 plus minus 22 by 2, and from this we get two values, which is 9 and minus 13. So from this also we have got minus 13. So now we are not able to conclude that which of them is the common root. So this M1 method fails over here. We are not able to derive the correct value of k. There is ambiguity between both 77 and 117, but definitely only one of them will be correct. We are not able to determine which one. So we need to go for the method M2 in this by using the relation that we have derived, and then let us see what is the answer that we get. So now by using M2, for which we will need the relation which we have derived, Let us see what do we get. Do we remember the relation? By solving some of the questions, it will become easier and we can remember it afterwards. So in the first few times, you might require to create that particular diagrammatic thing and then you can derive. So here we get, let us also write A1, B1 and C1. A1 is 1, B1 is 6, C1 is minus 91 and we get A1 C2 minus A2 C1 squared equal to A1 B2 minus A2 B1 B1 C2 minus B2 C1. So now we will substitute all the values and then we will get minus K plus 91 squared equal to A1 B2, which means 4 minus 6, and this gives minus 6K plus 91 times 4, 364. Solving this, we get K minus 91 the whole squared equal to 2 times 6K minus 364. Now as you can see, this we have got a difficult quadratic in terms of K. If you actually try to convert it into a proper quadratic equation and then solve it to find out the roots, it is definitely going to be difficult. So why not do one thing, that we know that answer will be between either K can be 77 or K can be 117. How did we get this? By applying M1. But now you might ask, if we do not apply M1 and we directly go for M2, then how will we know what is the value of K which we need to substitute? Then you will have options. You will substitute one of the options and you will see which of them is satisfying over here. Otherwise, if the equation is not that difficult, then you can solve it yourself. In this case, we know that the answer will be in between 77 and 117. So let us try to substitute both of them. When you substitute K equal to 77, then you will be getting 77 minus 91, which means 14 squared equal to 2 times 84 minus 364. Now this looks definitely incorrect because left side is positive and right side is negative. So this is definitely not the correct one, which means we will be having K equal to 117. Let's try to substitute. 117 minus 91 will give 26 squared equal to 2 times 702 minus 364, and you will check out that yes, this indeed satisfies, which means K equal to 117 is the correct answer. And from where do we get that? By taking minus 13 as the common root. So by using method M2, this was not that much lengthy. We just applied this relation and we got a quadratic in which we substituted all the options that we had, and only one of them turned out to be satisfying it. And what was that? K equal to 117, which corresponds to minus 13 being the common root for the two equations. So this is how we can solve such problems. Let us also have a look at one more problem. Problem is similar but somewhat easier than the last one. We are having the same two quadratic equations in which C2 has been substituted with K, and we need to find out K is a root of dash, which means we do not have to find the actual value of K. We just need to return an expression for which K will be the root, which means in the same way that in previous question we had got K minus 91 squared equal to 2 times of 6K minus 364, something like this we had got. So we just have to stop over here instead of solving this entire equation and finding the value of K. So the problem is reduced by half. Let us directly jump to method M2 for this and see what is the result that we get. So first of all, let us note down all the terms: A1, B1, C1 and A2, B2, C2. We have 1 minus 7, 3 and 1 minus 14 K. as our 6 coefficients. So now we will apply the relation we have, that is a1c2 minus a2c1 the whole squared equal to b2a1 minus b1a2 with b1c2 minus b2c1. And in this relation we will now substitute all the values and we will be getting k minus 3 the whole squared equal to minus 14 plus 7 minus 7k plus 42. 14 thrice 42. So now this simplifies to k minus 3 the whole squared equal to minus 7 times 42 minus 7k, or we get k squared minus 6k plus 9 equal to minus 294, which is 42 times 7 plus 49k. So when we express it properly in proper quadratic equation, what do we get is k squared minus 55k plus 294 plus 9, that is 303 equal to 0. So this is the quadratic in terms of k that we have got, and this is what they had asked us, that k is the root of this particular quadratic equation. We do not need to find its value. In options we will be just given 4 quadratics, of which the correct one would be x squared minus 55x plus 303 equal to 0. Now for this quadratic, k will be the root satisfying it. So this is what the problem on common roots was there. Similar types of problems are asked from this particular topic. We will be practicing some more examples from the same topic as well.